Okay, so we're almost down to the end. This week is the last week that will feature new material. So 6-1 today, and then 6-2 on Wednesday, and then on Monday I will be reviewing for the final exam. So practice test is already out there. If it's not, it should be accessible. If not, please let me know. And that's what I'll be going over on Monday. Okay. So here we have our new chapter 6, dealing with orthogonality. I have some definitions, and some of these things you would have seen in Calculus 3, well, Math 169, but I imagine that review is warranted. So suppose we have two vectors, u and v, that are in the same space in Rn, so they both have n components. Then familiar operation would be the dot product, which we'll refer to here as the inner product, which is a more general term. So for vectors in Rn, the inner product you get by multiplying corresponding components and then adding them all up. So the dot product of two vectors of real numbers is just a single real number. So if u1 v1 plus u2 v2 all the way up to un vn. Now, if the inner product turns out to be 0, then we say that the vectors are orthogonal. So geometrically, such vectors would be perpendicular. So this is something that you would be able to visualize in a 2- or 3-dimensional space. So more broadly, they are perpendicular orthogonal in n-dimensional space if the inner product is 0. The other term that we need is the length or magnitude of a vector. It's also referred to as the norm of a vector. So this is standard Euclidean length. This is something that you would have seen sometime in calculus also. So it's because it comes from a distance formula. So it's the distance between the endpoint of a vector u and the origin, which would just be the sum of squares of all the components, and then you take a square root. So basically, n-dimensional version of Pythagorean theorem. But it's also equal to, based on this formula here, the square root of the inner product of a vector u with itself. So this notion of magnitude will be useful. All right, so the thing to remember is that inner product of a vector with itself is also the length or magnitude of a vector squared. Okay. So now as we get into the problems, here we're given two vectors, w and x. So let's ask for our these two inner products, and then this ratio of them, which will just come directly from these. And this will relate to projecting a vector onto another, which we'll see in the next problem. So inner product of a vector with itself, that's just going to be the sum of squares of all the components. And then the inner product of two different vectors, so x and w. When the vectors are real, which they will be in any problems that we have here, the inner product is commutative. So it doesn't matter whether you compute x.w or w.x, just because of a commutativity of addition and multiplication. So Here we have the components of x, so 7 minus 3 and 2, multiplied by corresponding components of w, so 5 minus 2 minus 3, and then add them all up to get 35. Now the next problem calls for the same thing, computing, well, essentially the same operations, just roles of w and x are reversed. So the length of x squared, so the inner product of x with itself, and then the inner product of x with w. So that is just like in the previous problem. So then what's done after that is, okay, you go ahead and take the ratio of these inner products that you just computed, and then you're scaling that by x. And so then we're just scaling all the components of x by this ratio. Now, what's not actually talked about in the problem, but I feel like is worth mentioning anyway. So this quantity, where you take an inner product of x with w and then divide by x dot x and then multiply by x, that's what happens when you project the vector w onto x. Now, so what does that actually mean? It means that you are approximating w by a vector that's in the direction of x, because this whole quantity, this vector here, is parallel to x. It's a scalar multiple of x. So it is the unique scalar multiple of x that is closest to w. And what I've seen, and you may have seen in calculus texts, is how it's labeled. So it's a projection of w onto x. So a formula has x's all through it, except in this one spot here where the vector you're actually projecting onto x is given here in the inner product in the numerator. One thing I want to point out is with these kind of operations, since we have components being multiplied and then all of those products added up, there's nothing you can do here to simplify this, just because this is a kind of product operation. You cannot cancel the x's, can't do anything like that. Now in the next problem, you're given this vector, and I just pulled this from my labs of random entries that it puts in this vector, and it happened to choose 3 over 3 instead of simply putting it as 1. But so we're trying to find a vector that has the same direction as this one, but is a unit vector. In other words, it has a magnitude of 1. So all we do is we go ahead and compute the magnitude of this vector, so square root of sum of squares of all the components, which we can simplify a little bit. And then if we divide the vector by this magnitude, the result will be a vector that has the same direction but has a magnitude of 1. And here they want an exact expression involving radicals instead, because if they do not ask to round to 2 decimal places or anything like that, so be sure to provide exact expressions instead of rounding. All right, so this one says compute the magnitude, divide by it, that's your unit vector. Okay. Distance between two given vectors. All that means is finding the magnitude of their difference. So we go ahead and subtract these vectors, and that just means subtracting corresponding components. So 0 minus the minus 2, minus 6 minus the minus 1, 4 minus 9. So those are the components of the difference. And then you're just going to take the magnitude of this vector that is the difference. So then we do the same thing, square the sum of squares of all the components, and this is the distance between them. Okay, here we're given two vectors and supposed to determine if they are orthogonal. So all we do is take the inner product of them. So we're multiplying corresponding components. So 12 with 1, 4 with minus 4, and then 4 with 1. And once you work everything out, you find that the inner product is 0. So when the inner product is 0, then the vectors are orthogonal. So if you were to plot these points in three-dimensional space, and so vectors emanating from the origin to the point U and the point V, you would see that if everything is to scale, that vectors U and V are actually perpendicular to one another in free space. Okay. Now here we're giving these two vectors, and it asks for various expressions. So inner product of U and V, magnitude of V or length of V, length of U squared. So that just means the dot product of, or inner product of U with itself. Length of V squared, so that would be the inner product of V with itself. And then you can compute the sum and take the length of that. So here we go ahead and compute the inner product. So 4 times minus 7, and then minus 6 times minus 2, and then 4 times 4. And we end up with 0. So vectors U and V are orthogonal or perpendicular. And then inner product of U with itself, so that's just sum of squares of all the components of U. And then we do the same with V. And then for the magnitude of the sum, we go ahead and compute the sum of U and V. So in that case, we're just adding corresponding components. So 4 with minus 7, minus 6 plus minus 2, and then 4 plus 4. So this is a sum. So this vector here, minus 3, minus 8, and 8, that is U plus V. And then we do the same thing, inner product of this vector with itself. So we're squaring, taking a sum of squares of all the components. And here's our result. So this is related to the familiar Pythagorean theorem. That is, so you can think of it as being like a n-dimensional version of it. That if you have two vectors U and V in n-dimensional space, then when is the sum, when is the length of a sum equal to the lengths of the individual vectors? And the only time that happens is if the vectors U and V themselves are orthogonal. So in that case, the length of a sum squared is equal to the sum of the individual vectors' lengths squared. But only if this is true. In fact, what I can do is make a more general statement than this. So if I have a length of sum of vectors, so that'd be the same as the inner product of the sum with itself. Now, using properties of the inner product, it follows has a distributive property to it. So I can break this up. Inner product of u with u plus v plus inner product of v with u plus v. And then I can do it again with this vector. I can distribute u through this u plus v. So I have u of u plus u of v plus, and then over here, v dot u. And then v with v. So you think of it as foiling also. That works with the dot product. Now, dot product of, or inner product of u of itself, that's the length of u squared. Now here we have u inner product of v, v inner product of u. As I mentioned before, the inner product of real valued vectors, not complex, but real valued vectors, is commutative. These are the same. These are like terms that can be combined. So we end up with that. And then we have inner product of v with itself. That's the same as the length of v squared. So this is what you have in general. The length of a sum is equal to the squared is equal to sum of a length squared plus 2 times their inner product. So if the vectors u and v are orthogonal, then this term is 0, it goes away, and we're left with this. Now, are there any questions about these any of these 6 problems that I've covered? Okay. Now that hasn't taken very much time. So here's what I'm going to do. I have here the similar file for section 6.2, which is the final section. And those problems will not take very long either. So I'm going to make a spontaneous change here. And I'm just going to go ahead and cover those problems. So then what that will enable me to do is spend Wednesday's class talking about the final. The final is going to be longer because there's also more time for it. So it's a 2-hour test, whereas before you had 75 minutes, one class period. So there are more problems. There's there's I believe 15 problems altogether. So what I will do is start covering those on Wednesday. If I happen to finish all of them on Wednesday, then great. There will be no need for class on Monday. If not, then certainly everything can be wrapped on Monday. But I'll open a room for that by covering the 6.2 problems now. So what I need to do is unshare this and then share the other one. Come on. Okay. Okay, here's the other one. Also dealing with orthogonality and focusing more on that. So here we have 3 vectors, and the question is asking, are they orthogonal? So what you need to do for a set of vectors to be orthogonal is if you took the inner product of any 2 distinct vectors from this set, so first of a second, or first of a third, or second of a third. So since we have 3 vectors here, there are 3 possible pairs of distinct vectors you can have. If all of those inner products, all of them, are 0, then the vectors are orthogonal. So that's all I do here in this first problem is look at the 3 possible pairs of distinct vectors that we can have. So first with second, first with third, second with third, and go ahead and compute all of these dot products, so multiplying corresponding components and adding them up like it's done here. And it turns out in this case, all 3 of the inner products are orthogonal. All 3 of the inner products are equal to 0. Therefore, all possible pairs of distinct vectors are orthogonal. So the set of vectors as a whole is orthogonal. So that's how we define a orthogonal set of vectors of whatever size, is if any pairs of distinct vectors are orthogonal too. It's generally not easy to tell if 2 vectors are orthogonal just by looking. And sometimes you can, for instance, if certain components are 0. But one thing I want to point out, if you look at these 2 vectors right here, when you're taking their inner product, the third components will produce nothing because there's a 0 here. But then look at what we have here in terms of the numbers. We have 1, 2 here, and then -2, 1 here. So, in other words, you're getting these components by swapping these 2 and then negating 1. Whenever that happens, that's one situation in which you have orthogonal vectors in the 2-dimensional space. That if you have 2 components swapped and then only one of them is negated. So that's one situation that leads to orthogonality. This next one relates to what I was just talking about in the previous section, the vector projection of one vector onto another. So here we've given these 2 vectors, y and u. So the goal is to decompose y into a sum of 2 vectors, where y is in a span of u. Now, the span of a single vector is just all possible multiples of that vector. So in other words, the vector y hat needs to be a multiple of u. And then what's left, z, is needs to be orthogonal to u. Okay, so the thing is, if we choose y hat to be some multiple of u, we can't guarantee necessarily. We have to be sure of what's left over, because once we get y hat, then z is just going to be y minus y hat. We have to choose y hat, the multiple, in such a way that z is orthogonal to u. So to figure out what the correct multiple of u will be to go into y hat, so we stipulate that y hat is a constant times u, and we don't know what c is. Out. Now, this is not something you have to repeat when doing this problem, but I want to show you where the correct formula comes from. So y hat is of this form, and then z inner product of u must be 0. But what is z? Z is y minus y hat. So this inner product here must be 0. So then I break this up into 2, but then I use the fact that y hat is equal to a constant times u, and I fill that in here. So in other words, this expression, y inner product of u minus this unknown constant times the inner product of u with itself, that has to be 0. So now the 0 is all the way over there, so I'm just going to fill it in here. 2 must be equal to 0. So this equation has to be solved for c. So we just go ahead and solve this, and here's our formula for c. So the correct multiple of u is this right here. And this is what came up in the previous section, the vector projection of y onto u. So this is a formula well worth remembering, because it's introduced in the last section, but it comes in handy in this section. So this is how you get y hat. It's actually the best approximation of y by a vector in a direction of u. Now, once you have this, getting z is straightforward. You just subtract y hat from y. So now all that's left, we have our formulas. So really, you can just jump straight to this point. This is your formula for the answer to this problem. So now you just compute all of the required inner products for this fraction here. So that's our constant c, and then multiply that by u, which is 7 minus 7, and that is our vector y hat. So this is the best approximation of y by a vector in a direction of u. So any multiple of u has to have these two components negatives of one another, because that's what u. Once we have y hat, we just subtract it from y, and this is our vector z. So this vector z, because of how we computed y hat, is guaranteed to be orthogonal to u. And you can see if you did this is a multiple of u. So if you took the inner product of these two vectors, you can see that that you would in fact get 0. So this problem is a bit more elaborate than some of the other ones we've seen. So any questions about this one? Now, what was done in a previous problem is useful in this problem. Here we're given two vectors y and u, and there's a distance from y to the line through u in the origin. So what you do is you decompose y the exact same way as in the previous problem. So y has a multiple of u, z is orthogonal to u. Once you do that, then the distance that's being asked for is just the magnitude of z. Because we're trying to get to the shortest distance from y to this line that passes through u, that goes and has a direction of u. So the point on that line that's closest to y is y hat, because y hat is the best approximation of y by a vector to direction of u. So then you can think of z as being like the error. It's the distance between y and this line that has a direction of u, which is also the same direction as y hat. So then you just proceed as in the previous problem. Z is y minus y hat, and here's a formula for y hat from a previous problem. So for that, we need these two inner products. So those are computed here. And then once we work everything out, then we have our vector z. So basically, you've redone the previous problem right here. The only thing that's added on to it is to compute the length or magnitude of z, which turns out to be 3/5. So this is why this vector projection formula is good to keep in mind. That's useful in a number of problems. And then the last one, we have 3 given vectors, and asks, are they orthonormal? Now, the first problem in this section asked if a set of 3 vectors was orthogonal. Orthonormal is a step beyond that. So a set of vectors is orthonormal if 2 conditions are satisfied. If the vectors are all orthogonal to each other, so that's like in problem 1 in this section, and they must be unit vectors. In other words, they must have a length or magnitude of 1. So what this means is we actually have to compute inner products of all vectors in the set with each other, including themselves, because we need that to check everything. So if I take the inner product of u1 with itself and u2 and u3, and then inner product of u2 with itself and u3, I don't have to take an inner product of u2 with u1, because that's the same as u1 dot u2. I already have that. And then finally u3 of itself. So these are all possible combinations of not necessarily distinct vectors from a set. And then let's take a look at what we find. The inner product of each vector with itself is 1. So u1 with itself, u2 with itself, u3 with itself are all 1. So all of these vectors are unit vectors. But if we look at distinct vectors, u1 of u2, its inner product is 0. u1 of u3, inner product is 0. u2 of u3, inner product is 0. So the vectors are orthogonal, and they're all normalized to have a unit length, or length of 1. So because both criteria are met, orthogonal meaning unit length, this is an orthonormal set of vectors. Now, one thing I'll point out in the wording of a problem, if it says only orthogonal, normalize the vectors to produce an orthonormal set. Now, this was not necessary with these particular vectors, but I want to account for that possibility. If the vectors had been orthogonal, so that would mean that inner products of distinct vectors were 0, but inner products with themselves were not equal to 1. Then there would have been an extra step, and it's called normalizing a vector. Okay. So for example, suppose inner product of u1 with itself had not turned out to be 1. Then you'd have to take the square root of that to get its length. And then you would divide u1 by that length, and then u1 would be a unit vector. So that would be the only thing missing if they are orthogonal but not orthonormal. Are any questions about these problems? Well, that's the end of all the new material for the semester. So I will begin and not necessarily conclude, but we'll see how that goes. Begin covering the practice final exam, which will deal with, it's not comprehensive, it's covering all material we've seen from chapters 3, 5, and 6. So determinants, eigenvalues and eigenvectors, and inner product and orthogonality that we've seen today. So I'll be discussing those problems beginning on Wednesday. So I will end the recording at this point. If anyone has questions, they can stick around. Otherwise, you're free to scram.